Okay, this analysis is nearly identical, or it's very similar. Same sort of reasoning processes we use for the quarter circle of a line. Now we have a quarter circle of an area. And the way we look at it is we've already figured out the centroid of a triangle. Well, the triangle formed by the origin to the end, to the radius, and then crossing this distance, RD theta, and then back to the origin. That's a triangle. And we know that here's the fat part of the triangle. The centroid is 1/3 of this length from the fat edge, So it'd be right here. And then you can get an expression for the centroid, the location of the centroid here. Then we do an integral of RD theta. So it's x times 1/2 r times the base times the height of the triangle. Well, x times dA, this x tilde times dA, and the integral of y tilde times dA. Okay, and A is going to be 1/2 r squared d theta. Okay, dA, 1/2 r squared d theta. And here's the locations of the centroids. Centroid, r squared d theta over 2. And we just get, oh, come on, you silly machine. There we go. And of course, r is a constant in this case, so we just have integrals of d theta. They'll cancel each other out. Cosine theta, and I forgot about, let's see, where does the cosine theta come in? How do we get that? That's right. So here's x max is going to be r cosine theta, so 2/3 of that. Same thing with y max. Okay, let's go back and take a look. So we'll get these integrals then. This integral is 1. This integral is pi over 2. And so we will get 4r over 3 pi. This integral is 1. This is pi over 2. Anyway, same answer. So we get the centroid of a quarter circle area. And there we go. Next one. So this has some interest. We're going to take a look at this a couple different ways. So again, here's the centroid of the differential area. The area, so integrate from 0 to x, 0 to 1 meter of x. dA is going to be y times dx. Okay. Centroid times dA, y dx. Okay. Y equals x squared, so we get x cubed dx over x squared dx, 0.75. Now, for the integral y, we take the centroid times y dy. Well, we can express y's in terms of x's. So we just do that. Our variable of integration is x, so we have to convert y's to x's. Same thing down here. And we'll get a different answer. We'll have x to the 5th over 5 times 1/2 divided by, which is 1/10, divided by 1/3. Or there we go. There's the answer. Now, you can look at it a little differently. This is a little more complicated. So this time we're integrating y is 0 to 1. And x bar is going to be x plus 1 minus x over 2. Y bar is just going to be y tilde, I should say. Y tilde is just going to be y. So just keep these in mind. Do the same sort of thing. 1 plus x over 2. dA is 1 minus x dx. Yes, it is. Remember, here's the length 1 minus x. And dx, dy, dy. So the area is 1 minus x dy. Yeah. Okay. Now, 1 minus x times 1 plus x is 1 minus x squared equals y. So there you have that. So it's just going to be 1/2 minus y squared, 1/4, or 1/4. Integral on the bottom is just going to be 1 minus let's see, that's y, that'd be y to the 1/2 power. So it'd be 3/2 over be y to the 3/2, which is 1, divided by 3/2. So let's take a look at that. Come on, you silly machine. There's the tools. Okay. Integral y to the 1/2 dy equals y to the 3/2 over 3/2. Now, for the limits of integration going up to 1, or I'm looking at the bottom now. Okay, 2/3. 1 minus 2/3 is 1/3. So this integral evaluates to 1/3 and 1/4. Now previously, we got, oops, let's keep going, 0.75 meters, doing the integral this way. Here we get 0.75 meters going the other direction. Same kind of reasoning here. Equals the integral y dy is going to be 1/2. The definite integral, I should say, 1/2 meter, or 1/2 meter squared, minus 1 over 5/2, or 2/5. That's 1/10. And then on the bottom, we're going to get 1 minus, oh, we already did this one, 2/3 equals 0.1 over 1/3 equals the same answers we got before. There we go. 0.3 meters, just like before. Okay. Now, let's see what my timing looks like. Timing looks like I should probably quit right about now. We'll go on to another video.